Okay, this is problem 3. An environmental group conducted a study to determine whether crows in a certain region were ingesting food containing unhealthy levels of lead. A biologist classified lead levels greater than 6.0 parts per million as unhealthy. The lead levels of a random sample of 23 crows in the region were measured and recorded. A stem plot of the data indicates that the population is approximately normal. The mean lead level of the 23 crows in the sample was 4.9. So we have a sample size, this at 23. This is the sample, the mean from the sample, this is X bar, and the standard deviation from the sample, S, is 1.12. The fact that this is from the sample tells me I'm running a t-test. Construct a 95% confidence interval for the mean lead level of crows in the region. All right, so first off, we only have one sample here, so we're going to run a one sample T. And we're supposed to do a confidence interval. Now, this part that I'm about to do something that's not required, but the assumption would be that the lead levels are not a problem. So if I were writing a null hypothesis, I'd say HO, and I'm going to say ML for mean lead equals 6. Because I said it was okay if it was 6 parts per million. The problem is, when do we get concerned? If the mean lead level is greater than 6. All right. And so we're going to have but we're setting up a confidence interval, and all confidence intervals are two tails, and we're going to have an upper and a lower bound. Please remember, all confidence intervals are two tails. So we're going to go define define ML. Let ML equal the true population mean lead level in crows. It doesn't look much like crows, but that's what it says. And by the way, because this has been a confidence interval, if you wanted to do it this way, that's fine, because technically that's correct for confidence intervals, just like we have here. All right. So I need to sit there and go, okay, my conditions are met. So you don't have to do anything about the conditions. But we need to write our formula, and we're going to have X bar 1 plus or minus T star S1 divided by the square root of n. So X bar plus or minus T star divided by S divided by square root of n. So we're going to have X, and we need S. We're also going to need T star. And to get T star, we're going to have our degrees of freedom. So let's go ahead and start trying to identify some of this information. Oh, and we also need our sample size. Well, they told us our sample size is 23, so we can go ahead and write that down. That was easy. This is 4.9, and our standard deviation is 1.12. Well, at this point, I don't know my T star yet, but I'm going to go ahead and plug in what I do know. So I know I have 4.9 plus or minus. We're going to leave a space for T star. And then we're going to have our S is 1.12 divided by the square root of 23. Well, for a one sample, degrees of freedom, unlike the two sample, is n minus 1. So we're just going to go 23 minus 1, which is 22. So now that I know my T star, I can go calculate my, now that I know my degrees of freedom, I can calculate my T star. And they asked us to make this based on 95%. All right, and that's kind of important to note as well. So second vars, inverse T, parenthesis, 1 minus 0.95, close parenthesis, divided by 2. Degrees of freedom in this case, 22. And I end up getting a T star value of 2.07, 2.0738. So I'm going to go ahead and write that here. And at this point, I can go ahead and calculate my interval. So here we go. We're going to calculate the interval. We're going to go second vars, excuse me, stat test. And we're going to scroll down to T interval. Our X bar, we said was 4.9. Our S was 1.12. And our N was 23. We wanted a confidence level of 0.95. And so we ended up with 4.4157 and 5.3843. Now, what I notice is 6 is up here. All right. So 6 is above it, and that's going to be important. So 6 is way up here. So at this point, we need to go and write our, we need to define our confidence interval. We need to give our, explain what it is. And we are 95% confident that the true population mean of lead in crows lies within the interval 4.4157 all the way to 5.3843. All right, so every single one of those so anything in there is a plausible mean. It could be as low as 4.4 or as high as 5.3. So if I'm making a picture of this, any value between 4.4157 on the low side to 5.3843 on the high side is plausible. Anything in here is plausible. Anything outside is not plausible. So what else did they ask us? Is it reasonable to assume that the mean level consumed is 6 parts per mole? That was part A. So we ran the interval. So we had to construct the interval. We have to answer that question. And it is not reasonable. It is not reasonable to believe that the mean level is 6 or more, because, well, 6 is up here somewhere, right? Because our confidence interval is below 6. Now, if our confidence interval had been above 6, yeah, it'd be possible. If it contained 6, it was possible. But because it's below 6, it's not possible. So if it had contained it or had it been above it, that would have been possible. All right. So that answers part A. Part B, what type of error? Well, we wanted to know whether or not it contained it, which would have been, it's not equal to 6, it's more than 6. All right. So is it more than 6? And the answer is no, it's not more than 6. So in this case, we failed to reject the claim that there were 6 or more parts per million. The only type of error would be a type 2. Why? Failed to type 2. All right. Once again, in this particular case, our interval was below the critical point, so we didn't have to worry about it. All right. We failed to reject a claim that there were 6 or more parts. Now, sometimes you're going to have to read and you're going to have to apply logic. It's like, you know what? It didn't contain the bad number. So consequently, that's a good thing because 6 was a bad number. All right. If we contained 6, we would have said, oops, it's possible that there's 6 parts, but here there wasn't. All right. Thank you for watching that one.